Hey guys, let us now do one example on double integrals in general polar region. So in this example, we want to find the volume of the solid that lies under the paraboloid z equals x squared plus y squared above the xy plane and inside the cylinder. Right, first of all, let us try to sketch the various surfaces bounding the region. Let me start with the paraboloid. Well, this is a bowl-looking surface opening up towards the positive z-axis. Alright, and the vertex of this elliptic paraboloid is at the origin. Now let us sketch the cylinder given by the equation x squared plus y squared equals 2x. After completing square, we have x minus 1 square plus y square equals to 1. This is a circle centered at the point 1, 0 with radius 1 on the xy plane. So if we ignore the z-axis for the moment, we're going to have a circle here of radius 1 centered at the point 1, 0 on the x-axis. Since z is missing in the equation, we have to raise the circle vertically upwards and downwards to form the cylinder. Next, we are going to combine these surfaces and visualize the solid whose volume we need to find. And here's a picture of the solid that we're looking at. So it's a solid sitting on the xy plane because the question says the solid must lie above the xy plane. So the bottom surface of the solid is the disk of radius 1 centered at 1, 0 over here. And the top surface of the solid is part of the paraboloid. In fact, the cylinder will intersect the paraboloid in a closed curve. And that part of the paraboloid will be the top surface of the solid. Right, to find the volume of the solid, we can make use of a double integral. Namely, the volume, as we have seen last time, is equal to the double integral of the top surface, which must be given in terms of x and y, over the bottom surface of the solid. And this bottom surface must be a region coming from the xy plane. Right, in our case, the top surface comes from the paraboloid. So the integrand of this double integral is the expression x squared plus y squared. And let us call the bottom surface D. Alright, so let us now describe the region D in terms of polar coordinates. Notice that the boundary of this region is given by x squared plus y squared equals 2x. Recall that in polar coordinates, the left hand side x squared plus y squared is equal to r squared, whereas the right hand side, the term 2x can be replaced by 2 times r cosine theta. After rearranging, we have r squared minus 2r cosine theta equals 0. And factoring out the common factor r, we have r times r minus 2 cosine theta is equal to 0. Hence, either we have r equals to 0, in which case there's only one solution, which is the origin, or we have r minus 2 cosine theta equals to 0. Well, in fact, the case r equals to 0 can be included inside the second equation, since when theta equals pi over 2, then 2 times cosine pi over 2 is 0. In other words, this equation alone can be used to describe the boundary of our region D. Alright, so let us now describe the region D in terms of the polar coordinates. Let me start with the polar angle theta. To find the range for theta, we need to look at the rays coming out from the origin, cutting through the region D. For example, the positive x-axis is such a ray that cuts through the region D. Now, by increasing the angle, we are going to get a bunch of rays cutting through the region D until the angle is equal to pi over 2. So it seems all the angle between 0 and pi over 2 must be included inside the range for theta. However, this only covers the upper half of the region D. To cover the lower half, we need rays starting from the negative y-axis. That will be given by the equation theta being equal to 3 pi over 2. And now, by increasing the angle starting from the negative y-axis, we have a bunch of rays cutting through the region until we arrive back at the positive x-axis, which is 2 pi in this case. Well, we can combine these two sets of inequalities by observing that the angle 3 pi over 2 can be represented by negative pi over 2. In other words, the negative here it says that we measure the angle from the positive x-axis in the clockwise direction. Do you follow me? And likewise, 2 pi can be replaced by 0. So this way, this set of inequalities can be combined together in the following, where theta is bounded below by negative pi over 2 and above by pi over 2. Right, next we are going to determine the range for the variable r, which is the distance of our points from the origin. And for this, we are going to fix a particular ray cutting through the region D and look at the points on this ray which must be included inside the region D. So for example, if this is a fixed ray cutting through the region D, and the range for the variable r will be determined by the distance, or rather distances, of the points on this ray that is inside the region D. Well, it seems we have to start from the origin, because this is a point inside the region D. And by going away from the origin on this ray, it seems that we need to include all the distances starting from 0 until we reach the boundary of the region D, because beyond the boundary the points will not be inside the region D. So the longest distance on this ray is when the variable r reaches the boundary curve, but that is precisely when r is equal to 2 cosine theta. Remember, the equation r equals 2 cosine theta is the equation representing the boundary curve. And on this particular ray, when theta is fixed, that will be the upper bound for the variable r. And hence, we have arrived at the range for the variable r, describing the region D. So together with the range for theta, we have obtained a description of D in terms of the polar coordinates. And in fact, this is a general region in polar coordinates. Alright, so let us now compute the volume of the solid. Well, this is the double integral of x squared plus y squared over the region D. And by converting this double integral to polar coordinates, we have the following iterated integrals in terms of r and theta. So here we have replaced dA by r dr d theta. And the variable theta is placed outside because this is the variable which is bounded by constants. Namely, we have negative pi over 2 in the lower bound and pi over 2 in the upper bound. And furthermore, the variable r in the middle is bounded between 0 and 2 cosine theta. And of course, the integrand x squared plus y squared has been replaced by r squared. So after evaluating the inner integrals, we have the following integral in terms of theta. Right, to continue the calculations, we need to expand on the terms cosine theta to the 4. Well, remember the identity cosine 2 theta being equal to 2 cosine square theta minus 1. After rearranging, we can write cosine square theta as cosine 2 theta plus 1 over 2. And therefore cosine theta to the 4 is actually the square of the term here on the right hand side. So substituting this back into the previous equation, we are going to get the following. And so after some simplifications, we arrive at the following integrand. Right, again we need to get rid of the square term by applying the identity again. This time we're going to apply the identity by replacing theta with 2 theta. So doing that, we're going to get cosine 4 theta being equal to 2 times cosine square 2 theta minus 1. And after rearranging, we can write cosine square 2 theta as cosine 4 theta plus 1 over 2. And this is the term that we're going to substitute back into our equation. And doing so, we're going to get the following resulting integral. And after some calculations, we'll arrive at the final answer, which is equal to 3 pi over 2. Okay guys, that's all for now. See you next time.